Okay, so welcome to this next video in the Theory of Probability playlist. In this video, what we're going to do is study the gamma distribution, which is extremely related to the gamma function. So the topic for this video is the gamma distribution. Okay, so the gamma distribution has two parameters firstly. So what one writes x is distributed gamma, and then you have two parameters, usually denoted a lambda. Okay, but obviously you can use whatever symbol you want. So this is the setup. We have our abstract probability space here, and we have some random variable, which is denoted big X, which is mapping the outcomes in this abstract probability space onto the positive, well actually the strictly the positive real numbers, so not including 0, open interval at 0 end, onto plus infinity over there. Right, so it maps it onto the positive real numbers, and if we say that x, this random variable, is gamma distributed a lambda, then the PDF of this random variable, f big X as a function of little x, so this is just defined on the the positive real numbers. Everywhere else it's going to be 0, so I'll write that firstly. It's going to be 0 if x is an element of negative infinity to 0 and including 0, and it's going to be equal to 1 over gamma of a, where that's the gamma function evaluated at this value a, times lambda x to the power of a times e to the negative lambda x divided by 1 x there. Okay, so that is going to be the PDF if x is an element of the positive real numbers, so from 0 to infinity. Okay, so that looks quite a formidable PDF. And firstly, what we're going to study is the case where lambda is equal to 1, because that's simpler, and then we're going to see how these more general, the more general case where lambda can be any real number, it's going to have to be a positive real number, sorry, I should have said that. Lambda needs to be greater than 0, and obviously the gamma function is only defined on positive numbers as well, so a and lambda are both going to be greater than 0, strictly greater than 0. The reason you need a to be greater than 0 so that this gamma function, remember, the gamma function is only defined on the positive numbers, so I'll just remind you of what the gamma function is. The gamma function of, let's say, some value little a is equal to the integral from 0 to infinity of t to the power of a minus 1 e to the negative t dt. So that's the definition of this, and it's only defined if a is greater than 0, because this integral is only going to converge to some finite value if this exponent here is greater than minus 1, which is the equivalent statement that a is greater than 0, because when we integrate, remember, some negative exponent, providing the exponent is more positive to the right, if you like, of negative 1. When you integrate it, obviously you're raising the power by 1, so it's going to go to a positive number. It's going to have a positive power when you integrate it, and that results in the integral not blowing up, basically, when you evaluate it at 0 back here. Okay, so a needs to be greater than 0 so that the gamma function is going to be defined. Lambda needs to be equal to 0, greater than 0, so that this thing here is a negative exponent, strictly negative exponent, so that this thing here doesn't blow up as x gets bigger and bigger, because obviously we need this to integrate, for this to be a PDF, we need it to integrate to 1, don't we, over the entire domain, which is negative infinity to infinity, but of course it's 0 over most of that. Okay, right, so initially what we're going to do is we're going to study the random variable x is distributed gamma a, but lambda is equal to 1. So we're going to restrict our attention to this gamma distribution. So if I write what the PDF of that function is, of that random variable is, and I'm just going to omit this bit here, I'm just going to write this one here, so I'm just going to write the PDF with the understanding that we're talking about the interval, the positive real numbers, i.e. we just understand that it's 0 on all of the non-positive real numbers. Okay, so this is going to equal, we're still going to have the 1 over gamma of a, And then we're going to set lambda equal to 1, so we're going to get x to the power of a, and then we're going to have e to the negative lambda x, which will become e to the negative x, divided by x. And you might like to write x to the a minus 1, but there's a good argument for leaving the x like that, mainly because when lambda is more general, it's nicer. It's more it's nicer notation not to have to write lambda to the a, x to the a minus 1, instead to have the lambda of x to the a. It's more intuitive, so it's nice to leave it in this form rather than write x to the a minus 1. Okay, so there's our PDF on the positive real numbers. So let's firstly make sure that this is in fact equal to a PDF, which means that it needs to integrate to 1. Okay, so let's check that this integral here, f of big X as a function of little x, if we integrate that from, from negative infinity to infinity, but of course from negative infinity up to 0, this PDF is just equal to 0. So this becomes the integral from 0 to infinity of the PDF evaluated at this way x dx, where this is the PDF on the positive real number. So this is this thing here. So we can now just substitute this in for this here. Okay, so we get the integral from 0 to infinity of 1 over gamma of a x to the a. Now it might be better to put a minus 1 there actually. Then we'll see it more easily. E to the negative x dx. Okay, now the 1 over gamma of a is just a constant. It is just some number. You give me the little a, which is a fixed constant, a fixed parameter for this distribution. I will work out what gamma of a is. It's just a constant, so pull that out, 1 over gamma of a, and then we get the integral from 0 to infinity, x to the a minus 1 e to the negative x dx. But look up here. That is exactly the definition of gamma of a. If you work this out, x is now a dummy variable effectively because we're integrating it out. A is our fixed parameter up here. This is by definition the value of gamma of a. So this becomes 1 over gamma of a times this integral is just gamma of a. So this becomes just equal to 1. So that is why it is indeed a PDF. So this gamma of a1, where we've set the lambda parameter to equal 1, is most definitely a PDF. Okay, so that's good. Now I want to show you how the more general gamma distribution, where lambda can take on any value you like, is a transformation of this gamma distribution where the lambda parameter is equal to 1. Okay, so let me turn over. Right, so we have some abstract probability space here, and we have a random variable x, which is mapping you onto the positive real numbers here. Okay, so it's mapping you onto 0 to infinity like that. And this random variable is distributed gamma with first parameter a and second parameter 1. So the lambda parameter is at the moment equal to 1. Now what I'm going to do is do a transformation of this random variable. I'm going to take the function, I'm going to divide this random variable by the parameter lambda, where lambda is some positive real number. Okay, so lambda is greater than 0. Okay, and then what that's going to create me, and this is going to map you onto some more real numbers, and we'll think, in fact we'll think now about what real numbers it's going to map on. So okay, so if we think about mapping this function out, we're only interested in the positive real numbers. Our domain here is just the positive real numbers. So we're not interested in what this function is going to do to the negative real numbers. All we're interested in what it's going to do to the positive real numbers. Well, basically, it's going to divide them all by lambda. So and lambda is a positive number. So the gradient is going to be a positive number. Yes, the gradient is 1 over lambda, okay, effectively. But it's still a positive number because the multiplicative inverse of a positive number is still a positive number. So basically, it's going to look something like that, this as a graph. So this is x divided by lambda, where this is the x-axis and this is the y-axis. So basically, it's going to map the positive real numbers onto the positive real numbers. So you give me any positive real number in this, let's say, codomain here, I can find you a corresponding positive number in the domain over here, which was mapped onto it. Okay, so it's going to map you completely onto the positive real numbers. So we're then going to set this up as a random variable itself. So let's call it y, and we want to know how is this going to be distributed. So y is going to be the random variable x divided by lambda. So we now want to do transformation of the PDF of this random variable here so that we can now get the PDF of this random variable here. Okay, right. So let's do a bit of revision of transformations of random variables then. So what we want is the PDF of this new random variable big Y as a function of little y. Okay, what you can think about is we have the positive real numbers here. So here's 0 and you're going onwards like that. So this is now the Y space. So this effectively is this set here, okay, just drawn diagrammatically. We are now asking, what is the PDF going to be at some point, little y here? Well, by definition of the PDF, if we take some tiny little interval, delta y, then if I multiply this PDF evaluated at little y by delta y, that should be equal to the probability that it is within that interval, delta y, around that point y. Okay, so what we need to do is if we draw it on this graph over here, we have some point little y with now some interval delta y. What we need to do effectively is take the inverse image of that interval. So I've just gone along, said what did the point y plus delta y go to? It went down to here. What did the point y go? Where did the point y come from? It came from here. We need to work out what this interval is in the domain, and then we can use the fact that we know the PDF on this probability space and say, okay, if we want to work out the probability of that interval, we just evaluate the PDF at this point, let's call it little x, which is the inverse point of y, and multiply it by the size of this interval, let's call it delta x here, which is the inverse of delta y, if you like. Okay, right, so finding little x should be very easy because we know that big Y is equal to x divided by lambda, which means that little y is equal to little x divided by lambda. Whatever point little y was mapped onto, that point divided by lambda had to equal little y, because that was just the function, that was what this function was. So if we want to find the inverse image of the point y, we just need to find what real number divided by lambda is equal to y. So that's going to be equal to lambda, x is going to be equal to lambda y. So let's fill that in. X is equal to lambda y. Okay, now if we want to find out what the length of this interval here is, delta x, then basically it's very, very easy because it's a straight line. So if we want to find out what delta x is here, then we just need to know the gradient of this triangle, because we know what delta y is. So basically, if I zoom this up, because the picture is getting very small, so I'm zooming up, let me just highlight what I'm zooming up. I'm going to zoom up that little triangle there, okay? So we're going to get something that looks like this. Okay, so here is our original delta y, if you like. So this bit here was at the height, let me just draw the graph back again. So this bit here was at the height y here. So this was at the height y. This bit was at the height y plus delta y up here, so y plus delta y. Don't know why I'm drawing with the blue pen. So we now want to find out what this length is here. We know that this point down here is little x, which is equal to lambda times y. We want to work out what is the length of this side here. Well, the gradient of this line, we know that this line, if I continue on this line, then it should go through the origin like that. This line was equal to y is equal to x divided by lambda. The gradient, therefore, is 1 over lambda. Okay, delta y, how do we calculate the gradient of, how do we calculate the slope of a line? We take delta y and we divide it by whatever delta x is. So delta y divided by delta x should equal 1 over lambda. Now in this case we don't even need to use calculus because it's a straight line graph, so it doesn't need calculus. We don't even, this is true whatever you make delta y and delta x. They don't need to be infinitesimal values for this to be true. So delta y is therefore equal to 1 over lambda delta x. Okay? So if we want to work out what delta x is going to be, it's just going to be equal to lambda times delta y. Okay, right. So what we now have worked out is that the size of this, delta x, is equal to lambda times delta y. So what we now want to work out, what we're going to say is, because we wanted this probability space here to mirror the structure of this probability space, because that's the definition, that's what transformations of random variables are. You make the new thing mirror the same probability space structure as is on here, which means that the probability of this interval y to y plus delta y has to be the same as the probability in here of the inverse image of that interval, which is this interval lambda y, which is little x, to lambda y plus lambda delta y, basically. Okay, so if we want to work out what the probability of that interval is, then we can use the fact that we know the PDF on this probability space over here. So the PDF on here, because it was distributed gamma A1, so the probability density function of big X as a function of little x is going to be equal to 1 over gamma of A, then it was x to the power of A minus 1 e to the negative x, wasn't it? Okay, so that was the gamma A1 distribution. Okay, so now what we can say is, if we want to work out the probability of this interval, if we make delta y very, very small, then the lambda delta y is also going to be very, very small. So we can say that the probability of this interval is going to be equal to, so I'm going to write probability of this interval is going to be equal to the PDF of the function big X, because this interval now is within this probability space back here, because we took the inverse image of this transformation x divided by lambda. We took the interval y to y plus delta y, took its inverse image from here, we went back to here, and we're now saying, okay, if we want the probability of that interval in here, we take the probability density function evaluated at the point lambda y, and then we need to multiply it by the length of this interval, which is just lambda times delta y, okay? Because that's the length of the interval. Delta x is equal to lambda times delta y. Okay, so the probability of that interval, remember, was the PDF. By definition, it was the PDF of big Y evaluated at little y times delta y. So we are trying to work out what this PDF should be, basically. Okay, let me move this up. We're trying to work out what this PDF should be. We said, by definition, the PDF, if I multiply it by a tiny little interval, delta y, should give you the probability that within that interval. We've said, okay, take the pre-image of that interval in this old probability space back here, work out the probability there. That tells us that this PDF, whatever it is, times delta y should equal this PDF evaluated at lambda y times lambda delta y. So instantly we can cancel off the delta y's, and we get that this new PDF as a function of little y should equal the old PDF evaluated at lambda y times lambda. And of course we could have just plugged that into the formula that we worked out for transformations of random variables in the videos on transformations of random variables. But I think it's better to keep the intuition going rather than just using a formula. Okay, so now let's plug in what the now that I've just slagged off. So sorry, I shouldn't have said that on YouTube. Now that I've just okay, right, continue on. F of big X as a function of little x, if we evaluate that at lambda of y, then it's going to be, we put in lambda of y for x, so we get that it's equal to 1 over gamma of A. Okay, and you can't see this, so I'm putting in this formula down here. So 1 over gamma of A, and then we put in lambda of y to the power of A minus 1. Then we get e to the negative lambda y, and then we've got times this lambda at the end. So what I've just done is evaluated the original PDF at lambda y, and then multiplied it by this lambda down here, okay? So then what I get is, this is why it's important, why it's useful to split this out now. So we split it out into lambda of y to the power of a, and then have it divide it by lambda of y, and then we have e to the negative lambda of y times lambda, because then what we can do is cancel this lambda with this lambda, and what we get is it's 1 over gamma of a, lambda of y to the power of a, e to the negative lambda of y divided by y. So there's the PDF, and that's the PDF for the more general gamma distribution. So what we find is that big Y is going to be gamma distributed with parameter A and lambda, basically, with parameters A and lambda. Okay, so what we see is that this more general gamma distribution is just a transformation of this gamma distribution A1. So effectively it's nothing new really, it's just a transformation of a random variable here, of this random variable x is distributed gamma A1. So basically if you have a random variable taking an abstract probability space onto this PDF, then you can always find another random variable which will take it onto a more general gamma distribution, and the other way round works. So if you find that your probability distribution is distributed gamma A lambda, I can always find you a transformation of that random variable that will turn it back into a random variable that's distributed gamma A1 basically. So by studying the gamma distribution on A1, you also basically study this more general gamma distribution A lambda. Because this is just a transformation of this one, it's assured that it's going to be a correct PDF, that it is going to integrate basically to 1. You can check that if you like. In fact, shall we check it? Yes, we'll check it. We'll have a go at checking it. Let me get another piece of paper. Right, so let's check just to assure you, but I assure you it will work because it is just a transformation of the other random variable. So let's try and integrate this PDF between 0 and infinity, because of course this PDF is only on the positive real numbers, it's 0 everywhere else. So this integral from 0 to infinity of gamma of 1 over gamma of a, lambda y to the power of a, e to the negative lambda y divided by y, and then we're integrating it dy. We want that to be equal to 1. So the first thing that's crying out to be done is to transform, and basically what we're going to do now is we're going to undo everything that we've just done. We're going to undo the transformation we've just done. We're now going to substitute. We're going to let u equal lambda of y. So basically we're just undoing exactly what we've just done. And then we'll say that du is going to be equal to lambda dy. And then if we replace the limits of integration, so if y is equal to 0, then u is going to be equal to 0. If y is going to be equal to infinity, then u is also going to be equal to infinity. So the limits of integration stay exactly the same. We get the constant stays the same, 1 over gamma of a. We replace lambda of y with u, and then we get u to the power of a. We replace e to the negative u now, lambda of y is replaced by u. dy gets replaced with du over lambda, and now that lambda combines with that y from underneath, and we can now replace these two together to give us a u basically. And then combine that together with this over here, 0 to infinity, 1 over gamma of a, and we get u to the power of a minus 1, e to the negative u du. Then just pull out this 1 over gamma of a, and we get 1 over gamma of a, the integral from 0 to infinity, u to the power of a minus 1, e to the negative u du, and then that's just the definition of gamma of a. So we get that this is gamma of a over gamma of a, which is just equal to 1. So basically, by doing the integration by substitution, what we did is reverse the transformation that we did. Where we transformed to the PDF. They're effectively the exact opposites.